Welcome to English BookCast. You know, if you're really digging these deep dives and finding them valuable, we'd love for you to be a part of the channel. Liking, commenting, sharing these explorations, with other folks. It really does help the channel grow. And it lets us bring you more of these deep, in-depth conversations.
Absolutely.
So welcome back to another deep dive. Today we're jumping headfirst into the world of artificial intelligence.
Oh, it's a fascinating one.
Yeah, it's moving fast, isn't it? And our guidebook, our roadmap, is a book called Artificial Intelligence from Beginning to Date by Liu, Chen, and Wang.
Mm-hmm.
It's a pretty comprehensive text, I gotta say.
Mm-hmm.
And it really maps out, from those first sparks of inspiration all the way to the current cutting edge, frontiers of AI.
Yeah, it does a really good job of, laying out how the initial ideas have developed and sometimes stumbled, but, ultimately surged forward. It's a rich history.
Yeah, and our mission, if you will, in this deep dive is to really unpack those key milestones, the essential definitions, and I think most importantly, the core concepts that are presented in this book.
Right.
What we want to do is give you, the listener, a clear, a solid understanding of AI's development, where it stands today.
Yeah.
All without getting bogged down in, the super technical jargon.
Right. Keep it accessible.
Exactly.
Yes.
Think of it as your shortcut to grasping those essentials, hopefully sparking a few aha moments along the way.
Absolutely.
So let's begin at the very beginning.
Okay.
Some of those initial conceptualizations, the ideas that laid the very groundwork for artificial intelligence.
Yeah.
The book really highlights, and rightly so, I think, the work of McCulloch and Pitts back in 1943.
IQ43, yeah.
They had this concept of a brain-like machine, often referred to as the MP model.
Yeah, the MP model, it's a classic.
And it holds this distinction. It's, began the very first neural network model.
The world's first.
And I think what's really significant here is that this wasn't just, theoretical. It really fundamentally kick-started the structural study of the human brain.
From a computational perspective, which was revolutionary at the time.
So this MP model, this first attempt at a neural network, it wasn't just some kind of abstract idea floating around. It really set a direction for future research.
It was a blueprint, a rudimentary one, but a blueprint nonetheless. And the book emphasizes how their exploration of connection mechanisms, the idea of interconnected nodes processing information, really, blossomed into what we now recognize as the connectionism school of thought in AI.
Yeah.
That core principle, the parallel processing within a network of interconnected units, it's a powerful idea.
It's a recurring theme, isn't it? Throughout the history of AI.
Absolutely. It keeps coming back.
Fascinating. So this connectionist approach, that was one of the early ways of thinking about AI. Were there other influential ideas kind of bubbling up around the same time?
Oh, definitely. The book devotes a good chunk to, cybernetics.
Okay.
Particularly the work of Norbert Wiener.
Right.
His 1948 book, Cybernetics, or the full title was Cybernetics, or Control and Communication in the Animal and the Machine.
Right.
That was groundbreaking. It really connected our understanding of the nervous system with fields like, seemingly disparate fields like information theory, control theory, even logic and computing.
So cybernetics was kind of looking at the fundamental principles of how information is processed and systems are controlled.
Exactly.
Whether they're biological or artificial. How did that specifically impact those early stages of AI research?
It was a big influence. Wiener's cybernetics, it kind of gave birth to what we'd call the cybernetics school of AI. It's also tied closely with the behaviorist school of thought. The idea was to, understand and then ultimately replicate intelligent behavior, but by focusing on what you could observe, inputs and outputs, drawing parallels between how animals and machines control their actions based on feedback from the environment.
Yes.
If you have, connectionism inspired by the brain's structure and then behaviorism looking at observable actions, it really sets the stage, for AI to emerge as a formal field of study. And the book then moves into, kind of a chronological overview of AI's development.
Yeah. Let's get into that. So it talks about this initial period of, really intense enthusiasm. There was this widespread optimism, wasn't there?
Yeah.
Almost a belief that machines would achieve human-level intelligence, like very rapidly.
Yeah, around the corner kind
Yeah.
of thinking.
Yeah, but the book points out that this was followed by what's now often called the AI winter.
The AI
A
warning.
real slowdown, reduced funding and a lot less progress. What actually led to this downturn? What happened?
Well, a few things, I think. Primarily, there were limitations in the problem-solving methods. The tools just weren't there yet. And early systems, they had structural limitations too, that prevented them from tackling real-world problems effectively. And, a lot of those ambitious promises, they just couldn't be delivered on with the technology of the time.
Right.
Some problems, they were just too hard to crack with the initial approaches. Or sometimes the solutions, they were for oversimplified versions of problems.
Those weren't really AI, were they?
Not really, no. And there were issues like, managing something called combinatorial explosion. That's where the number of possibilities just explodes during a search that really limited practical application.
Makes sense. Makes sense. So after this slowdown, did the field eventually kind of pick up again?
Oh, yeah, it did. The book calls this next period the knowledge application period.
Knowledge application. Okay, tell me more.
So this was roughly from 1970 to 1988. There was a shift. Researchers started realizing that maybe instead of, building general purpose intelligence right away, they could focus on systems that used specific, expert knowledge to solve problems within particular areas.
I see.
And this is where we get expert systems.
Expert systems.
The book gives examples like Dendrol. That was designed to help chemists figure out the structure of molecules.
Okay.
And then there was MYCIN, a medical expert system to help doctors choose the right antibiotics for infections.
Wow. So these were actually practical, useful applications?
Yeah, many of them were used, at least experimentally.
Oh, wow.
The book mentions Prospector, used in geology to find minerals.
Okay.
CastNet for diagnosing glaucoma, a Mesa-Sama for math, symbolic math computations. And then there's R1, ELAS, ACE, used in things like computer hardware design, telecom networks, all sorts of areas. It was proof that encoding human expertise into programs could actually, tackle complex real-world tasks.
Yeah, real proof of concept.
Yeah.
This era, it led to the formalization of a really key concept in AI, right?
It did. At a big AI conference in 1977, Edward Feigenbaum, he formally proposed knowledge engineering.
Knowledge engineering.
It's basically the idea that building intelligent systems, to perform at an expert level, well, it required a process, a systematic way to acquire and represent knowledge from human experts.
Yeah, like distilling that expertise into a machine.
Exactly.
Yeah.
And he even predicted that the 1980s would see a huge boom in expert systems. And to a large extent, he was right.
He was ahead of his time.
Yeah.
Okay, so a shift from that general problem solving to leveraging specific knowledge. And then the book goes on to what it calls the integrated development period of machine learning. Sounds like another big turning point.
It was a big one.
Huh.
Around 1986, there was a new focus on algorithms that could learn from data directly, not just, relying on programmed knowledge. And it was more integrated, Different learning approaches started to kind of merge and influence each other.
Interesting.
On one hand, you had this resurgence of neural networks helped by things like backpropagation algorithms.
Right, backpropagation, that's pretty fundamental in training modern neural networks, right?
Oh, absolutely. It was a game changer. It allowed for training much more complex, deeper networks, unlocking their potential for learning really intricate patterns.
Okay.
And at the same time, in symbolic AI, there was this emphasis on growth-oriented learning. Systems could learn and refine their knowledge over time, often building on existing, domain knowledge.
So instead of starting from scratch each time.
Right. They weren't ignorant anymore. They could learn from experience, become more sophisticated.
That's a huge shift. So these two approaches, neural networks and symbolic methods, they were both advancing, maybe even sharing ideas.
Exactly. And then, then we get to the modern era, deep neural networks.
The big leagues.
Yeah. The last decade, it's been marked by incredible progress with deep learning. The book mentions the Google Brain project in 2012 as a real turning point.
Yeah, I remember that.
This large-scale deep neural network trained on massive data sets, using tons of computing power. It achieved incredible results in speech recognition, image recognition, really tough tasks.
Yeah, that was groundbreaking.
And it showed the power of these really large, deep neural networks with multiple layers to automatically learn hierarchical representations from raw data.
It seemed like a real spark, that ignited a wave of innovation and investment.
Yeah, it really did.
And there's another big achievement in machine learning that the book points to that really caught the public eye, didn't it?
Oh, yeah, the victory of machine learning algorithms in Go.
Go the game.
Yeah, Go, the game.
Okay.
Specifically, AlphaGo.
Right, right.
It mastered the game, and it defeated world champions. It really underscored just how much progress had been made, especially in handling, complex reasoning, strategic planning.
It's amazing when you think about it. From those early theoretical ideas to these incredibly capable systems today. And the book, it delves into some of the fundamental concepts that underpin all of this progress.
Yeah, it lays the foundation.
Let's start with machine learning itself. How does the book actually define this core concept?
Well, it draws on Herbert Simon, a real pioneer in AI.
Okay.
He defined learning as a process of self-modification. And in the context of AI, machine learning, it's the ability of a system to improve its performance on a task over time through experience.
Through experience, okay.
Yep.
What about the basic structure of a system that can actually learn in this way?
So a typical learning system has three key components: the environment, the knowledge base, and the execution part.
Okay.
The environment, that's the source of data, the feedback. The knowledge base is where the information, the rules, the existing knowledge lives.
Okay, I gotcha.
And the execution part is where the system actually does stuff, performs tasks.
Makes sense.
But the key, the really important part, is the learning component. It takes the information from the environment, analyzes it, and uses it to update the knowledge base. That's how the system improves.
So the quality of the information, that's got to be crucial, right?
Absolutely. The book stresses this. The richer, more relevant the information, and the smaller the gap between that information and what's already in the knowledge base, the better the learning.
I see.
But if you give the system, tons of irrelevant or noisy data, learning becomes much harder.
It's like trying to learn a new language from a broken radio.
Yeah, exactly. This system has to work so much harder to filter out the noise, to generalize from limited examples.
Right.
And the book also talks about different machine learning strategies.
Okay, let's get into those.
So first, there's inductive learning. It's basically about generalizing from specific examples, to form rules or conclusions. But the book points out induction always involves some uncertainty. You can never be completely sure your generalizations will hold true in every future case.
Right, there's always that element of the unknown.
Exactly. Then there's explanation-based learning. That's about taking knowledge that might be unusable and turning it into something useful for problem solving.
Oh, okay.
Then you have learning by analogy, where a system basically reasons by comparing to past experiences, finding similarities. And finally, there's reinforcement learning, where an agent learns by doing, getting rewards or punishments for its actions.
Interesting. So it's learning by trial and error, essentially.
In a way.
So those are some really fundamental approaches, the building blocks.
Yeah, they're at the heart of a lot of applications.
And another core concept that the book gets into is knowledge representation.
Yeah, that's a big one.
How do we actually, encode knowledge in a way that an AI system can use?
Right, it has to be structured. So the book presents several methods. One is logical representation. It uses formal logic, things like predicate calculus, to represent facts, relationships, rules.
It's very precise, very unambiguous.
Exactly. Then you have semantic networks. It's a graph-like structure, nodes representing objects, concepts, and the connections between them representing relationships. The book specifically talks about binary semantic networks, which can use hierarchies and slots with values, to describe things.
I remember those diagrams as semantic networks. It's like webs of ideas all connected together.
Yeah, exactly. And building on that idea are knowledge graphs, which, companies like Google use extensively.
Okay, those huge now.
They are. They describe entities in the world and the relationships between them very explicitly.
Okay.
Building a knowledge graph, it involves, getting the information, fusing it together from different sources, and then processing it for things like making inferences, answering queries.
So it's a more sophisticated way of representing knowledge, drawing on multiple sources.
Right.
What other methods does the book talk about?
Well, the last one in this section is frames. They describe objects or situations by using slots, which hold values or have characteristics.
Okay.
Frame systems are often hierarchical with inheritance, so specific concepts can inherit properties from more general ones. And the book also touches on ontological commitment, which is, it's how a knowledge representation system basically sees the world, its assumptions about how things are structured.
So it's about the underlying philosophy of how knowledge is organized.
Yeah, in a way.
And with all these methods, logic, semantic networks, knowledge graphs, frames, I imagine the choice of how you represent knowledge
Mm.
has got to have a huge impact on how an AI system can reason and learn.
It's foundational.
And speaking of reasoning, the book also explores knowledge search and reasoning techniques.
It does. It talks about state space search, which is, well, is how AI systems tackle problems by searching through different possibilities. The problem is represented as a graph, with states and transitions between them defined by operators.
Operators, okay.
These operators, they're like functions that can generate the next possible states. And the search process is about, systematically applying these operators to move from an initial state towards a goal state, which is the solution.
Okay, but how do they search efficiently? These spaces can be huge, can't they?
They can be enormous. The book distinguishes between blind search and heuristic search. Blind search, it just explores systematically, no guidance.
Okay.
But heuristic search uses, well, heuristics, rules of thumb, estimates, to guide the search, to focus on more promising paths. It often uses evaluation functions to assess the cost of reaching a state and the estimated cost to reach the goal.
So these heuristics, they provide some intelligence to the search process. What about automated reasoning? How do AI systems actually, draw new conclusions from what they already know?
So the book digs into automated reasoning, focusing on logical formulas. It describes this process of converting predicate formulas into a clausal form using a series of transformations. And it talks about resolution reasoning, which is a way to derive new clauses from existing ones by finding and eliminating contradictory elements.
It's a very formal, very logical approach.
It is. But then what about the real world, right? Where things aren't always certain, things are fuzzy. How do AI systems deal with that?
Yeah, good question.
The book addresses reasoning under uncertainty. It mentions how early expert systems, like MYCIN, used certainty factors.
Okay.
And then it introduces probabilistic reasoning, using concepts like conditional probability and Bayes' theorem to deal with uncertain information.
So it's a way for AI systems to deal with probabilities, not just absolutes.
Exactly.
It's really amazing, all these different aspects of creating artificial intelligence.
It's multifaceted, that's for sure.
And the book, it wouldn't be complete without discussing where all these ideas are being applied. What are some of the key areas it highlights?
Well, there's natural language processing, enabling computers to understand and use human language. There's automatically proving mathematical theorems, and automatic programming, trying to get computers to write programs themselves.
That's vicious.
It is. And then there's intelligent retrieval of information, scheduling and planning systems, and of course, robotics.
Robotics, yeah, that's huge right now.
It is, from industrial robots to sophisticated autonomous systems, unmanned vehicles, drones, service robots, space robots, underwater robots, even smart factories.
That's a whole world in itself. What else?
The book covers expert systems, of course, and intelligent control automation, which are becoming more and more common. Then there's pattern recognition, machine vision, neural networks, although those are often considered separate fields now, and machine game playing. That's always been a big area, a way to test AI. And then you have distributed intelligent agents, artificial life, even specialized AI programming languages.
It's really broad range.
It is. And AI is finding applications in fields like bioinformatics, biological robotics, genomic research.
Oh, it's touching almost every field.
Yeah, the book gives specific examples too. Systems for solving equations, playing chess, designing circuits, synthesizing languages, diagnosing diseases, controlling aircraft, robots. It really highlights how AI is impacting so many areas.
It's everywhere.
Yeah.
And with all these applications, especially with machine learning, data must play a massive role.
It's fundamental.
And the book discusses this, the interplay between data and AI.
It does, and it talks about how data itself has evolved.
Oh, interesting.
So it went from classic structured data to big data, then to live data, real-time streams, data from the Internet of Things, and then you have these new computing architectures, GPUs, FPGAs, cloud computing, the potential of quantum computing, AI chips, and 5G networks. All of these are fueling AI by making it possible to generate and process massive amounts of data.
And this leads us to a question we actually received from a listener.
Okay.
What is the relationship between machine learning and data?
That's a great question. The simple answer is machine learning learns from data. Data is the raw material, And machine learning algorithms are the tools that refine it, that extract knowledge, that make predictions, that drive decisions. The quality and quantity of data, they directly impact how well a machine learning model performs.
So data isn't just input, it shapes what the system learns.
Exactly. Data is the experience that allows machine learning to improve without being explicitly programmed for every situation. It learns patterns, correlations, relationships. It allows systems to adapt and evolve without constant human intervention. It's the fuel for the learning process.
That's a really clear way to put it. Data is fuel for learning, and it explains why advancements in data are so crucial to the progress we see in AI.
Absolutely.
Well, we've covered a lot today, the history, the concepts, the applications of artificial intelligence, all based on this book, Artificial Intelligence, from beginning to date.
It's been quite a journey.
It has. And seeing how fast AI is evolving, especially with machine learning, here's a final thought for you, the listener. What do you think the next big transformative application of AI will be?
I don't know. What will it be?
Something that will impact our lives in ways we haven't even thought of yet.
It's an exciting thought. The possibilities are endless.
Thank you so much for joining us on this deep dive. We'd love to hear your thoughts, your reflections, any questions you might have. And for our next deep dive, we're going deeper into machine learning. We'll be looking at the main strategies and the basic structure of machine learning based on Chapter 4 of this book.
Can't wait.
Looking forward to it. And that concludes this deep dive. You've been listening to English BookCast. Please keep participating, share our explorations, help the channel grow. Until next time, thank you and goodbye.